Good afternoon, everybody, and welcome. I'm Andy Miller. I'm a professor here in the Department of Geography and Environmental Systems at UMBC. This is the opening seminar in our fall 2021 seminar series. We do record all of these seminars with the speaker's permission, and after we get the recording back, those are posted on the YouTube channel of the Center for Social Science Scholarship here at UMBC, and we've also put the link up on our department webpage once we have that. So all our seminars will be virtual, at least for the fall. I don't know what we're doing in the spring yet. We're going to see how it goes in the fall. So our next seminar is in a couple of weeks. We're trying to iron out a couple of last details, and then we'll put out an announcement about that. We have a number of others lined up. The schedule is not fully published yet, but it will be coming soon. So for our first seminar today, we're very excited. We have a distinguished speaker from the University of Leipzig, and I'm not going to do the introduction because we've asked our own Dr. Lorraine Reamer, who is a member of the research staff at the Joint Center for Earth Systems Technology, and who's also affiliate research faculty in our department. So Lorraine is a close colleague of Dr. Quas, and she is going to introduce him to us. So Lorraine,
thank you,
the floor is yours.
Yeah, thank you. I'm Lorraine Reamer. I'm affiliated with GES and a research professor in JSET. And it's a great pleasure that I'd like to introduce Professor Johannes Quaas. Professor Quaas, as Andy said, is a professor at the University of Leipzig. He has his PhD from École Polytechnique in Paris. He's been a visiting scientist at the Max Planck Institute of Meteorology, the Hadley Center in the UK, and at NASA GES in New York multiple times. I met Johannes when he was a young, upcoming rising star in climate science. He was always a pleasure to work with and also very annoying because he kept telling us everything we were doing wrong, but he's right. And it's good to see him come into his own and achieve the status of being a senior scientist now. It makes me very old. I'm probably a grandmotherly scientist. Professor Quas is a climate scientist. He's interested in pushing the boundaries on cloud processes and cloud climate feedbacks. He uses both large-scale models and satellite observations to do his work, where we cross paths in terms of the satellite observations. And what he's really known for is aerosol cloud radiation interaction and how that impacts climate. And it's interesting because if you follow the IPCC assessment reports from the beginning, there was no mention of aerosol. Then they mentioned aerosol radiation effects, and then they moved into aerosol cloud radiation effects. So it's been a progression in the science as during my lifetime. Anyway, Professor Quas is here as representing the 6th assessment report of the IPCC, of which he's a lead author of one of the chapters. Thank you for coming. I'm going to.
Thank you very much, but I should correct this in particular thanks to all the good things which you and correct things which you did, and of course much of the progress which the field has seen in recent times is thanks, Lorraine, to your work and one of your colleagues of teasing out knowledge about the state of the atmosphere from satellite, which is an invaluable source, of course, of information when it comes to global climate and the state of the climate system. So this is also why first of all, summarizing the headline statements and headline findings by the IPCC report, I'll give it a certain focus on the role of clouds and aerosols, because that is the particular research topic that, for example, Lorraine and I are interested in, and also, of course, where the expertise lies. And so you'll see particularly also the contribution which I did, of course, on the basis of the research done across the world in climate science to this assessment report. So what I'll do is I take first maybe 2/3 of the slides and half of the time or so by presenting to you what is compiled by the IPCC as a whole as the headline statements and the key figures in that report, and then dig deeper into the report itself and show you some of the figures which I think are of particular interest, and as I said, in particular in this field of clouds and aerosols and their role in climate. So let me start by quoting to you the headline statements, the headline findings of this IPCC report. IPCC is for the Intergovernmental Panel on Climate Change, and after recapitulating these headline statements, I'm also going to explain a little bit how the IPCC and the progress process of its assessment reporting work. So these are the key conclusions. Recent changes in the climate are widespread, rapid, intensifying, and unprecedented in thousands of years. And this statement actually relies on the chapter I have been contributing to, and I'm going to show you where this is from: the widespread, the rapid, the intensifying, and also the unprecedented. Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. That's looking into the future and looking into the perspectives of reaching this target by the Paris Agreement. It is undisputable that human activities are causing climate change, making extreme events, including heat waves, heavy rainfall, and droughts, more frequent and severe. Here I'm also going to show, there's two aspects to it. First of all, the statement that these extreme events get more severe, and there's observations to demonstrate it. I'm going to show these. And there is the second attribution aspect to it, that we can demonstrate that human activities are the cause, and with that, of course, we mean the partial cause, at least, of these events. Climate change is already affecting every region on Earth in multiple ways. The changes we experience will increase with further warming. There's no going back from some changes in the climate system, by which, of course, we look at the inertia of the climate system, and with that we mean in particular the very long timescales at which the ocean in particular operates. However, some changes could be slowed and others could be stopped by limiting warming. To limit global warming, strong, rapid, and sustained reductions in CO2, methane, and other greenhouse gases are necessary. This would not only reduce the consequences of climate change, but also improve air quality. And in particular, this air quality aspect is something, again, that is in the domain of what we do research on when it comes to the aerosols. Okay, so these are the headline statements which came out of the IPCC, and I'll come back to that in my last slide later. You might not be very surprised by several of these, and climate change, of course, is not a recent topic. We know about climate change now since a decent while, but some of these statements are stronger than they used to be in past assessment reports, and that is, of course, because climate change was not very well addressed by societies, and so climate change actually, and that was the first statement, accelerated in the past years. Let me take a break from these statements, and later I'm going to go a bit deeper into the science from which these statements derive. But let me say a few words that I was asked also to tell you a bit about this IPCC process. First of all, what is the IPCC? It's an intergovernmental panel. So this IPCC plenary, which is on top here, consists of representatives by governments. And in total, it is, I think, 90 governments or 92 governments that send representatives to this IPCC plenary. So it's intergovernmental. It is an agreement by governments to perform this research into climate. And this is under the umbrella of the World Meteorological Organization and the United Nations Environmental Program. So that's the plenary, that's the governments, but the governments then mandate a bureau and a secretariat to actually conduct the IPCC duties. Of this bureau, the key people form the executive committee, and these people on the bureau and the executive committee, they are scientists from climate research relevant fields, and they are elected by this IPCC plenary. And since the first assessment report, the IPCC has formed 3 working groups. This is the working group 1 that looks into the physical science basis of climate change. Working group 2 looks at impacts and then also adaptation and vulnerability. And working group 3 looks at mitigation of climate change. And then there's also a task force on national greenhouse gas inventories, since of course, from the IPCC process followed the need to reduce greenhouse gases, and from these agreements on reductions of greenhouse gases, of course, comes the need to somehow monitor or look into these greenhouse gas reductions. So why do I show this? This is because when we say there was a new IPCC report, then what we really mean is that working group 1, the working group on the physical science basis, has finished its 6th assessment report. So it's the 6th in a series. The first one was in the early 90s. And approximately every 7 years, there was a new assessment report, and now we are number 6. And that was true for working group 1. And since, to a certain extent, working group 1 lays the scientific basis for also researching into impacts and mitigation, that's because of that, working group 2 is a little bit delayed, shifted in finalizing their report, and working group 3 still a little later. So you will see coming IPCC reports in that sense, also in the coming months, of which followed is in about a year from now, follows then the synthesis report, which is the overarching full 6th assessment report with the contribution by all 3 working groups. But now the topic of today, and also the report which is published now, is the report by working group 1. And I should also say, IPCC is of course not a research body, but it is an assessment report, and by this one means to a certain extent a review, but an assessing review. So it values to a certain extent, evaluates the science and extracts from it the science relevant to new findings of climate change. And that is also very important, is that now we are at report number 6. So in particular, what was necessary in this assessment is to summarize and assess what's new since the 5th assessment report, so since 2013. And basically, we focused mostly on the past 7 years. And with that, of course, we have the authors, and this is the for each. One step which I wanted to explain further is each of these reports consists of individual chapters, and each of the chapters now has a number of lead authors, and 2 of them are the coordinating lead authors. And so that was my role, to serve as a lead author in one of these chapters, and that was the chapter on the observed climate change, the observations of past climate change, chapter 2 in this report of Working Group 1. Beyond these lead authors, there's a plenty of contributing authors as well, which we asked for additional help with writing the report. And then there is, and I'm sure those of you who look into physical climate science, several of you helped actually making this report robust by reviewing it. It went through public review 3 times, not public in that sense, but expert review. So in order to become a reviewer, you needed to register, and that registration required providing a reference or a few references of publications of yours, so that you identify yourself as an expert on the climate field, so that not anybody who could just well, destroy or at least sabotage a bit the process by putting in reviews without being an expert. So it was for experts, and also, of course, for people named by the governments to review this report. Some numbers, the total number of lead authors for this Working Group 1 report was about a bit over 200. And then, of course, it was paid attention that this list was a bit, at least, diverse, so from many countries, and also in terms of gender. Maybe it's interesting to also to see how do how do you become a lead author. The Intergovernmental Panel on Climate Change is intergovernmental. So the first is with the nations, so with the representatives of the different states, the different governments in IPCC. So the way it worked in Germany, at least, is everybody could volunteer to become a lead author. And then you would submit this application to the national IPCC office, and then the nations could screen, but they didn't in the case of Germany, but transmitted all these names to the IPCC Bureau, and the IPCC Bureau would select the lead authors, and they would pay attention that there was a decent diversity, not only in expertise, but also in geographical distribution and also in gender distribution. And then I highlighted the importance on relying, first of all, on research. So that was an assessment by many publications, and the importance that this is a peer-reviewed and expert-reviewed report. So each of us had to answer approximately 400 review comments, and that is, of course, a very important aspect of the IPCC, that the report itself is heavily reviewed, and there were, for each chapter, 2 review editors, independent review editors, who paid attention that we really did very carefully and well documented for each of these 80,000 review comments, documented our responses and answered to them properly. Okay, after this sort of section where I a little bit explained how IPCC works and how this reporting works, let us look into some of the results. And first, I wanted to show you the key figures from the report, and these are compiled by the IPCC Bureau itself. So what the IPCC centrally thinks are the key findings. This is the key figures from the so-called summary for policymakers, which is the high-level summary, executive summary, if you like, of the IPCC report. So one thing which is a little bit, I hope you can read these, because some of these slides are a bit small. So this is what they have stuff for making these figures, but I hope you can read it. If hopefully you have a big screen, then it shouldn't be a problem, but if you have a laptop, I hope you can read it. Anyway, I'll walk you through what is here, and of course the IPCC report is publicly available on the website. IPCC.ch, because IPCC has its office in Geneva in Switzerland. That's why it's CH, the top level domain here. And if you look at the here, you see it's the summary for policymakers SPM figure 1, so that's where you can see it. And this is corroborating the statement that human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. And we look at time on the x-axis here from the year 1 in the Common Era to present day. And you see the reconstructions of global mean surface temperature in decadal averages and uncertainty range, and then you see, and this is deviations from the time period 1850 to 1900. So 1850 to 2020 is considered the time period of climate change, of anthropogenic climate change, and that's also the time period where we have decent observations. And now a very important thing is, what is pre-industrial? So what is the state of climate before anthropogenic climate change kicked in? And it needed a pragmatic answer, because we need a stable and well-defined pre-industrial control, and that's why pre-industrial is defined as the average between 1850 and 1900. So it's a 50-year average. You could argue this is a time period when the humans already had a sizable impact on climate, on the climate system, but it's also a time period where we have measurements across the globe, not perfect, not like now. We didn't have any satellites, for example, but it is a time period where we could define it. So it might be sort of a bit smaller than it could be, but that's the deviation. So it's a deviation from them. And then you see, obviously, the rate of change and also the magnitude of warming is unprecedented in the last 2,000 years. And here's the warmest multi-century period, so average over a sizable time, because if you go down and go into the past longer, then it becomes, of course, difficult to quantify for individual years, but you see it's also outside the range of multi-century periods in more than 100,000 years. And the right-hand side answers the question, what's the cause? And this answer, of course, can come about only if we know what would have been had we not had human activities. And that can only be answered using models. Now, of course, we are in a good position in the climate, in meteorology, to know the fundamental equations that govern the atmosphere, and we solve these using models. And we could talk all day about the difficulties with the models, but it is also, of course, a blessing that we have these equations, because at least we have equations, so we can say what would have been. And that's in green, what would have been with only natural impacts on climate, that is the sun, and that's volcanoes. And then in orange, if you also include greenhouse gases and aerosols, and then you see that matches what was observed, and the one with only natural forcing would have been stable as probably expected. And here you see, even if you consider the uncertainties since the turn of the century or so, we clearly distinguish the two. So that's clearly, including all we know, humans are the cause of this one. The cause. What are the causes? And this is now in the second figure quantifying the observed warming, global observed warming in Celsius or Kelvin here, and that was about 1.1 degrees Celsius if you consider the period 2010 to 2019 and compare it to the period 1850 to 1900, as I said, the pre-industrial baseline. And now with a new method that's new in the sixth assessment report compared to previously, we quantify the influences of individual human activities in degrees of Celsius, so that from the former measure, which we used to use in terms of the energy budget, the so-called radiative forcing. Now, using emulators, these are translated into degrees Celsius, which is, of course, much more intuitive. And then we look into many things. Yeah, well-mixed greenhouse gases. That's this bar here, and there are several of them. That's the right-hand side figure: carbon dioxide, methane, nitrous oxide, halogenated gases, and nitrogen oxides. And then in blue, other human drivers, and this is in particular sulfur dioxide, organic carbon, ammonia, and black carbon. That is the aerosols. That's the effects of the aerosols. That's particles in the atmosphere compared to gases, which are in particular greenhouse gases. And then there's also land use, reflectance, and irrigation. That's had a slight cooling effect, in particular because the albedo was changed, and then aviation contrails, small positive forcing. Solar and volcanic, net zero over this long period, and then internal variability also over that long period, approximately zero. So if you sum up these effects, and that is an interesting finding, I think, and it's also new because that wasn't really the case before, is that it happens or over this now much longer period also compared to previously. Now these internal variability, solar and volcanic drivers, they average out to zero. So the total forcing is now exactly explained by anthropogenic activities. Climate change is already affecting every inhabited region across the globe, with human influence contributing to many observed changes in weather and climate extremes. And this is looking into individual regions across the globe, and this is schematically looking at North America, Central and South America, Africa, Europe, Asia, and Oceania. And well, this is basically just schematically looking at these extremes. Increase in red, decrease would be blue, but hasn't been observed, and then low agreement or no data, there's limited data in some areas. And then the confidence in human contribution, the 3 dots is high, etc. And then you see for hot extremes, that's what we look at here. For hot extremes, it's very clear there was a human influence, and there was an increase. Of course, maybe not super surprising. Heavy precipitation is something you might have seen in the news. We in Germany had a very devastating event this summer, so that was a heavy debate this summer in Europe, and particularly in Germany. It was really Belgium as well. It was really devastating. We understand very well that warming coincides with increases in heavy precipitation, actually exponential increases in heavy precipitation, and that's observed in many regions across the globe, nowhere a decrease. And in many cases, we can attribute it. Although, of course, precipitation is much more variable than temperatures. And then drought as well, a drought and increase, and that might be counterintuitive. Yeah, in precipitation increases, that's true for all precipitation, but in particular for the heavy precipitation. And at the same time, drought increases. And we can understand it by knowing that the pattern of evaporation minus precipitation intensifies in a warming climate. Yes, if I had more time, I could explain it. It's not very difficult to follow if one knows the fundamental equations. That this is what we expect, an increase in pattern. So that's why, in particular in the subtropics, for us, the Mediterranean region in Europe gets drier. Now let's look into the future. If we look into the future and look at the expected warming in the end of this century compared to the pre-industrial period, 1850 to 1900, and then the big uncertainty, which is not the topic of working group 1 of IPCC, is how do humans behave in the future? And this is the shared social pathways, SSP, the different hypotheses, how the future could look like, how humans could behave in the future. And the leftmost bar is always the total warming, and observed is a little bit darker usually. That's what we already have in the system, and then a bit lighter what's expected in the future, and then the contributions by CO2, non-CO2 greenhouse gases, aerosols, and land use. And overall, aerosols did cool, and also for the future integral thing is still a cooling, and then greenhouse gases warm. And yeah, you see, I mean, even with the most optimistic scenario, it will be difficult to reach the 1.5 degree target. And many scenarios would consider it's even not possible probably to stay below 2 degrees even in this century. What's regional? Yeah, looking at global mean is one thing. Looking at the pattern is the other thing. And here, what's done is only the pattern. So at the time, or when when the globe reached 1 degree, what was the observed pattern of temperature change? And here, compared to the simulations, we see basically that the simulations and the observations coincide, which corroborates our understanding, of course. And then we can look into the future. Lower left is 1 point at the future time, of course, of 1.5 degree, maybe in the 30s of this century, at 2 degrees and at 4 degrees global warming. And then you see this particular pattern emerging, that land areas warm more than the oceans is something which we also theoretically understand and which we expect. It's not just a transient effect due to the heat capacity. And the polar regions warm more than the lower latitudes. And that's true already now for the Arctic, and it will become true and more true for Antarctica as well as climate change progresses. And similarly, also the pattern of precipitation, that's now from simulations. And you see what I already alluded to, this idea that dry get drier, wet get wetter, so that the pattern of precipitation minus evaporation intensifies, and you see the precipitation gets reduced where it's already pretty dry, in the subtropics in particular, and it gets intensified where right now it is wet. And I should say this is in relative changes, so that's why also very dry areas like the Sahara area are particularly visible on this view graph. So I talk more than I thought. Sorry, I didn't give this talk very often. I think I have about 5 to 10 minutes left. Let me. Well, sorry. Here's one more from the overall compilation of IPCC, and that is this finding, which already was part of the 5th assessment report, and it's now corroborated, is that it is the cumulative CO2 emissions on the x-axis that almost linearly translate into the global warming. So each additional gram or kilogram of CO2, of course, matters for global warming because it scales. The global warming simply scales with the CO2 we emit, and then we can basically see in history that was true, and in the future, according to the models, that's also true. But there's no reason not to trust this. So let me dig a bit into the, after talking about the summary for policymakers, let me dig into a few aspects of the report itself, about more details of the report. And that's basically on the basis of what we looked at in the observed changes. It is part of chapter 1 though, and it looks at this idea that we see it in every aspect of the climate system. In every aspect, we see an Earth system that is consistent with a warming world. We see it, of course, in the atmosphere in the CO2 concentration, normalized always to 2015. No, sorry, the differences are normalized to 1950. Here we see the increase in CO2 concentrations since pre-industrial. Precipitation increases in global mean temperate precipitation, or rather northern hemisphere temperate land and southern hemisphere subtropical land. you see the increase is, of course, precipitation much more noisy than for example, temperatures. Glaciers, reductions, significant reductions in glaciers across the globe. That's part of the cryosphere. Global mean surface temperature we saw before. Global mean sea level, and that is of course interesting, because the sea level is an integral metric of the warming, because the ocean expands due to additional heat and loss of ice on land, glaciers in particular. And then the ocean heat content, that is how much more energy the ocean stores, basically the ocean temperature, but in energy units. And global sea level, ocean heat content, and our knowledge about what do we expect the changes in CO2 and other constituents in the atmosphere to do to the energy budget. All these are now consistent, which is of course also very interesting and important closure of all our knowledge between these different aspects of climate change. So that's a figure which I compiled on the basis of data which Lorraine at least helped produce. That is now looking at the aerosols, and on the bottom is actually the data, Lorraine, from you and your team and your colleagues. That is looking at the aerosol optical depth since the MODIS instrument and also the MISA instrument are in space since 2000. And this is the linear trends for that 20-year period. And you see, of course, as we expected for aerosols, it's a noisy field. So crosses means we do not find significant trends. But where we find significant trends, what's interesting now is that since the turn of the century, we see a reduction. So we see cleanup of the cleaning of the air, of course, due to air quality legislation, in particular in North America, I mean, where you live and where I live in Europe as well, but also other parts of the globe. And then we see increases in parts like the Indian subcontinent. And where we see these changes, they also have the little circles. We also see consistency in the trends from surface observations. This is from the Aeronet. The circles are from the Aeronet, and you see they are pretty much consistent. That's looking at the fine mode here on the right-hand side. That's the smaller particles, and anthropogenic aerosols are predominantly in these smaller particles, and you see that the signal is even much more pronounced. And on top, the curves that's trying to look deeper into the past, and that's from ice cores in the Arctic, Russia, Europe, South America, and Antarctica for sulfate, and then for black carbon, that's soot. It's even, I think, two more stations which you could look into. And in particular, where we have the influence by the industrialized nations, America in the Arctic scene, Europe, Russia, that we see the ramp up of the aerosol emissions from the pre-industrial times to about the 90s, and then a reduction since then. And that we see in the two different aerosol types. Let me skip. Oh, well, let me give one aspect to it. This is what we expect then from these changes in terms of the global mean Earth radiation budget. That's what we call the effective radiative forcing, and we see the strong positive, ramping up positive forcing by greenhouse gases, carbon dioxide in particular, and we see the cooling by the aerosols, which leveled off and now turns less negative. So it's a net positive thing since the turn of the century. That's the aerosol forcing. And the rate of change, and I think that's the point I wanted to make. The rate of change was always positive all the time, but it gets more and more positive. That's this acceleration. And the reason is we increase the emissions of CO2 that accelerates the concentration of CO2. That's one aspect. But also we take out the aerosol, we take out the cooling effect increasingly, and these two reasons lead to this acceleration of climate change. So that's these aspects. Maybe I briefly skip over. Maybe this aspect. This is this aerosol forcing, and Lorraine mentioned that that's a field where she and I are particular experts, and if you look at the last assessment report, this aerosol forcing was less negative than what we think now it is. That's one thing. The distribution between what's the role of aerosols alone and what's using the lever of clouds has changed. So now this cloud lever we think is larger, and the uncertainty range is a little narrower than it used to be. And sorry, I didn't prepare very well. I'm sorry, skipping over slides is never a very good idea, but I can't help it because I run a bit out of time. Let me say something about the response of the climate system. So that is these feedbacks in the climate system. We have, if we have global warming, and that's for an idealized scenario where CO2, where we have a fourfold concentration of CO2, that's why the warming is very large. But once we do this, then we can decompose this warming into the individual contributions by processes that amplify or dampen the warming. That's these feedback processes. First of all, the radiative forcing, the change of the energy budget, of course, is the driving force of warming. And then part is taken up by the ocean. And then we have these feedbacks, the processes in the climate system that act in response to that global warming. And you see it's a positive number. So overall, they amplify, we have an amplification of global warming. If we only had CO2, we would expect, for this quadrupling, we would expect 2.5 degree warming. With these amplifying feedbacks, also considering ocean heat uptake, it's more than double this. And here's decomposed. The key thing is that water vapor in the atmosphere increases due to the warming. That's following those of you who are from a physics background, the Clausius-Clapeyron law, broadly speaking. And water vapor is a greenhouse gas, so that's the key thing. Lapse rate, it's how strongly temperature decreases with altitude in the atmosphere, and that dictates the strength of the greenhouse effect. Since it's slowing down, we have a reducing effect here. Snow and sea ice melt when it gets warmer. That reduces the albedo, so the fraction of sunlight reflected to space. That's a warming. And now, and that's, I think, very interesting, a conclusion here, the net cloud, the cloud response. Clouds are, of course, very important when it comes to the energy budget. The net cloud response is now clearly defined as positive. There's reasons why we know this now much better. But let me conclude with this graph from the IPCC report, because I think it is an important graph, and it is also a very interesting. Well, it's not a fancy science conclusion, but still it's a very important and interesting graph. And that is noting IPCC was founded in the 1990s, in the early 1990s, and the international community in 1992 at the climate conference in Rio de Janeiro in Argentina, that it was at that time that humanity decided we need to act against climate change, and it was on the basis of science. And that was on the basis of science by the previous generation of climate scientists, many of them of which are, of course, famous Americans. Suke Manabe in Princeton, Jim Henson at NASA GES in New York are two individuals one should probably name. But there were earlier people who did projections and did predictions as early as the early 70s. And if you look at all these predictions from former times, including also IPCC itself, FAR is the first assessment report, second, third, and fourth assessment report, and then look at the predictions from that past and look at in black the observations, then you see the previous generation of climate scientists, 30 years ago, and more than 30, and now up to 50 years ago, they were right. Yeah, people knew what's coming. And actually, they knew it's coming. I mean, the 1992, of course, they concluded we should act. Okay, with that, I'd like to thank you for your attention. There's, of course, plenty of channels to follow IPCC and read about this in more detail, but now I'm happy also to take a couple of questions, please.
I apologize. I had lost my mute button and could not find it. So what we've asked people to do, first of all, thank you for that. Really, it's fascinating. It's disturbing. It's, I think, something that we all need to hear more about. We asked people if they want to ask questions to post them in the chat, and we'll call on them in the order in which the question is posted. I'm going to pose one to get us started while we're waiting for other people to pose them, since you didn't have too much chance to talk about the effect of aerosols. But one thing that I wonder about, there's really two pieces. One is, if we do a better job reducing aerosol emissions, we are presumably going to make the warming problem more severe. And I'm guessing that the projections are accounting for that. The other question I'm wondering is that we're seeing an increasing number and severity of wildfires in many places around the globe. Certainly we're seeing it in the Western US. I presume that has a consequence in terms of aerosols in the atmosphere as well, and I don't know whether that's something that's been accounted for or not.
Yes, first, you're right. You're right. The reduction of aerosols, of course, will lead also in the future to further warming, additional warming. Part of which can be cancelled if at the same time we also work on the emissions, which we do typically, or at least in many cases, emissions of methane, because methane is much shorter lived than CO2. So methane we can, with decent actions, we can take out of the atmosphere in our lifetimes, or in shorter than our lifetimes even. Yes, so as you may guess, of course, there are considerations to maybe make even use of this fact that aerosols cool the climate, so-called climate engineering. But I think the bottom line is the overwhelming and increasingly so overwhelming aspect of drivers of climate change, so of course CO2, and of course aerosols are really bad for our human health. So there's good reasons to reduce them nevertheless. The other aspect that's a good, very interesting and actually exciting problem as well, also scientifically exciting problem, I should say, the problem of wildfires, some of which are so intense in Australia, for example, last year, so intense that they get all the way to the stratosphere. That's the area where, for example, also volcanoes emit the aerosols to, where they are long-lived, because that's the part where we have no weather, we have no clouds and precipitation, so there's no way to wash them out. So that's why they live very long. So it's exciting. On the other hand, of course, one should say, it is a bit like I haven't dwelt much on the volcanoes. A bit like the volcanoes, these can be very important, but typically on relatively short time scales. So also for volcanoes, you probably know, we haven't seen a substantial, a very substantial volcano, at least since Pinatubo 1991. So it is interesting and to be expected statistically, but we can't predict. At some point, a volcano will erupt, after which, of course, we might see a cooling for a certain period, but of course only for up to a couple of years. And similarly for the wildfires, unless we have a continuous wildfire that will not affect long-term climate change.
Thank you. We do have a couple of questions posted. First comes from Lorraine. Lorraine, you want to go ahead and unmute and ask the question?
Sure, thank you. Thank you, Johannes. That was really very good, very perfect. Did I see that the Sahara is predicted to get wetter?
It is, but this view graph was in percentage change, right. So it was the change divided by what we see today. and since today is close to
Nothing.
0, we divide by a small number. So yes, it's interesting to see, and who knows if climate change really continues. I mean, probably most of us as citizens, scientists, we would be interested, but as citizens, we hope not. But if maybe at some point it would be beneficial even for Sahara.
Yeah, and just quickly that the aerosol system keeps changing, and it's not just human, and that human has a piece of it. So it's hard to model what the future would look like. It's hard to know what it was back in 1850 also. So it's an interesting unknown.
Yes, yes. There's also the feedback, of course, because wind speeds change, and with that, of course, also the dust and sea salt. Yeah, very.
That's the sea salt, the fires, all of
Yes.
it. Yeah. It's hard. You had some other questions, so
It's
I'll
complicated.
pop out again.
So before I invite Emma to unmute and ask her question, I want to encourage others, particularly students, to post questions if you have them. There's a lot to think about here. We'd like to be able to ask Dr. Quas questions that people think of that are germane to the topic. So Emma, why don't you go ahead and unmute and ask your question?
Thank you so much, Dr. Quas, for presenting today. I was intrigued when you mentioned that this is the first assessment in which there's been quantification of human activity contributions in degrees Celsius. And I was curious, it seems like such an important thing to provide in light of that being such a huge driver. But what, in your opinion, is the biggest reason to include that and to look at that?
So I think it is a very important step in terms of communication and understanding. It's not so much in terms of science because the measure it is not qualitatively something different compared to what we did before we measured it in watts per square meter, so as perturbation of the Earth radiation budget. Which and now it's basically translated by our knowledge on how does the climate system respond to this forcing. So I think it is very interesting because it helps to much better understand what these numbers mean. But on the other hand, of course, it is not like we cannot go back and trace this also to what we knew before.
Okay, thank you. We have 2 more questions that have been posted. Yu Jing, do you want to unmute and ask your question?
Yes, can you hear me?
Yes.
Thank you, Dr. Quas, for the great talk. My question is about, from your perspective, how does the recent IPCC report guide the future research on the aerosol radiation forcing by the aerosol radiation interaction and the aerosol cloud interaction? Like, for example, like, are there any specific suggestions from the IPCC report that reduce how much the uncertainty of the aerosol radiation forcing can help to get a clearer prediction of the global warming?
So now I'm not. I guess we could talk long about what are the details and also the very not only details but really important processes which we don't know about. As you know, that's also my field, and we could dig deep. But if you want one answer, which is and since you asked also about the relevance to know better climate change, the key question is this lower bound of the aerosol forcing. So how negative could it possibly be? And IPCC and also our previous attempts to say what's the most negative aerosol forcing which we can think of, they did not rely on our process understanding. So they always relied on backing it out from what we did see as climate change. And since we of course see that the world has warmed, and it actually has warmed everywhere, we know the aerosol forcing cannot have been very, very strong. So because always the greenhouse gases were more important. But it's of course, to us as the aerosol forcing community, that's a bit annoying that we cannot say much better what is possible and what's not possible in terms of global aerosol forcing. So it would be very nice if we as a community could say, okay, it cannot be more negative than minus 1.5 degrees, minus 1.5 watts per square meter, for example. But we cannot. We cannot rule out minus 3 watts per square meter, really. Certainly not minus 2 watts per square meter. But that is impossible, we know, but we only know, unfortunately, because of other lines of thought. So, yeah.
Okay, yeah, thank you.
Thanks. Our next question comes from Anisha.
Yeah. Hi, Dr. Quas. Thank you for such a great talk. This is not really a question about the physical science basis of the report, so I'm sorry about that. But I was just curious if the working of the IPCC changed in response to how governments have or have not responded to previous reports. For example, in terms of the frequency of when it was published.
So since the IPCC is intergovernmental, and that is a bit circular, of course, because it's the governments themselves who decide, at least who decide on the frequency, and they have never. So after many of the past reports, the authors thought, well, we have enough knowledge about the climate system to act, and it is maybe no longer necessary to tell more details about the physical science basis. Which, by the way, I'm not sure that's true, because the more precise our predictions get, the better this is, of course, for maybe not for the general decision we need to reduce CO2, but for many other decisions. Well, the short answer is hasn't really changed very much. So these working groups were the same, and also approximately the way we addressed it. Now, of course, this working group 1 report, if you did look at past reports, you see it is much more concise and it's much more targeted towards the application, targeted towards what working group 2 on the impacts and working group 3 on the mitigation say. Much more on extreme events, on regional aspects, and much less on the large-scale aspects. So like the observations was only one chapter this time. But it helps, of course, also to understand things. But very broadly speaking, no.
Thanks. We have 2 more questions. I think that will allow us to close it out. So I'm going to call on Grace Rigsby first.
Hi, Doctor. So I am just curious. I know you are specialized in atmospheric and weather sciences, but I'm curious what led you to focus on aerosols specifically, and kind of like what led you to ask these specific questions?
So one of the very important problems which we had in climate science didn't come out so well on my last few graphs, but if one analyzes a bit more in detail, then you see there is a sizable spread in the prediction of the past, and if we go out to the future, then there is really a sizable spread in how much more warming do we expect, even if we know how we perturb the climate. That's the question of so-called climate sensitivity. The climate it is a relatively simple equation, if you like. The climate sensitivity is linked to the energy budget, the relative forcing, by the fact that we observed the warming. So the observed warming is explained by 2 factors. One is the net change of the energy budget, the net relative forcing, and the other one is the climate sensitivity. Now, if climate sensitivity is what we want to know, a way to know it is by knowing the net forcing. And people try to know climate sensitivity, like by looking at the climate change since the ice age, etc. But I think knowing the forcing is easier. And the reason is the CO2 forcing is well behaved. CO2 first order is well mixed in the atmosphere, and we know relative transfer. Yeah, that's not completely true what I say, but approximately. So the key uncertainty is the aerosol forcing. So if we know the aerosol forcing, we can back out from the observed warming, we can back out climate sensitivity, and we know much better where we're heading, even if we know how we as humans as a total behave. But come back, my answer to the last question, for that in particular, we would need to know what is the most negative aerosol forcing, and we haven't managed to do so. So maybe I haven't, or the field also hasn't succeeded in this.
Thanks. So although we know some people have a hard stop at 1, we've got one more question from a student, and then I think we should close it out with Bilal Demos, who's the director of JSET. So we had an introduction from JSET. We'll close it out with a question from JSET. So Ethan Cruikshank, can you unmute and ask your question? And then we'll go to the last question after that.
So my question was on whether
We're not able to hear you very well.
Irreversible impacts of climate change that you mentioned earlier on in your seminar, whether that was accounting for sort of mass carbon removal projects, or whether that was sort of too much of a pipe dream kind of plan, and these are more like realistically irreversible climate change impacts.
Yeah, so irreversible in the sense of really no way going back, and I do think that's not what we mean here. What we mean is well, under plausible scenarios. But you're right. I mean, we could imagine really returning the CO2 concentrations to pre-industrial by carbon dioxide removal. Right now there is no technology for that. There is no meaningful way we could do it. But of course, a very important aspect is a very important thing we need to all know about is that we will need these carbon dioxide removal techniques anyway. So the future will not work without removing CO2 out of the atmosphere by means. We have passed that threshold, if you like. We cannot just save CO2 emissions. We also need to take out CO2 from the atmosphere by whatever means. Yeah, it could be natural things, but then we need to, growing trees really and burning them, and then burying the CO2, the bioenergy, carbon capture and sequestration. But then we need to consider the threat to biodiversity and also nutrition. So if you could do it at a very large scale, or also, if you really like, solar radiation management, climate engineering, of course, could also do the job of, in the long run, making it reversible. But this is all on very long time scales. Right now, we have an energy imbalance at the top of the atmosphere, which means the ocean is heating up. The deep ocean is continuing to heat up. It's going to continue to warm and continue to expand. That's anyway in the system for many decades to centuries.
Thanks. So we're going to close out with a question from Bilal.
Yes, thank you. Thank you for a very nice presentation on behalf of JSET. But I wanted to poke you a little bit on, you referred to climate engineering. And a lot of us in JSET do work in dust-related stuff. So if Sahara is getting wet, is there a view of IPCC on creating our own dust? And more importantly, your view on the effect of that? Thanks.
Yes. I think most scientists do not like artificial interference with the climate system, because you saw me openly or not so openly sometimes talking about all the uncertainties. The climate system is a difficult to understand system. That's also, of course, why we love it, or we do science about it. If it was easy, then it wouldn't be interesting. So fortunately, it's complicated. But on the other hand, of course, our societies live in it, in the climate system, and then tinkering with it. We really should know exactly what's the consequences. And since we don't, I think that most scientists like the thought and like the ideas and like also to do research about climate engineering, but I don't know anybody who likes to actually see it done and rather not make it necessary. Of course, the idea is there could be scenarios where climate change really gets out of control. These are unlikely, fortunately, but or even highly unlikely, but could happen. And in which case, of course, maybe that's after all the better option.
Okay, thanks very much. This has been a fascinating event. I really appreciate you joining us for this seminar. And I know we have colleagues who have told us they could not be here, but we are going to post this recording once it's available so that other people can watch it. So thanks very much for your time. We really have enjoyed it and look forward to reading more in depth about what else is in the report. So thank you.
Thank you for the invitation. It was a pleasure and great discussion. Thanks.
Thank you, Johannes.